Hello everyone. In all the previous lectures of 3D elasticity, we have stated that whatever we were discussing, it was finally to build up to a situation where we'll be able to solve the Kelvin's problem. So finally we are here. I had briefly discussed the statement of the Kelvin's problem earlier. Let me do that in a slightly greater detail now. So we consider an infinite body. So I represent the boundary of that body in this fashion. It doesn't mean, of course, that this body is just limited to this boundary. Okay, so you understand that this boundary, it is just to mean that we do have some material here, but this boundary is just, way off into infinity. Okay, what we also say is that, so earlier I had mentioned that we had a point body force acting on this body. Now, what I as a slight generalization to that, what I will do here is to not consider a body like this, not consider a body force like this. Rather, what I'll do is I'll consider a body force which is perhaps like this, okay, acting at certain point, and I will consider a reference axis in this fashion. So let's say this is x1, x2 and x3, and what we say is that the position vector of the point where this point body force is acting, this blue colored arrow is acting, this point here. So the position vector of that point, what we say is this is xi vector. Okay, so now it has been set up in a general fashion. So going forward, what we'll do is we'll try to address this general form of the Kelvin's problem using the Popkovich-Neubauer representation. And whatever we had discussed in our previous lecture in relation with the solution of the Poisson's equation and the Dirac delta function, and then we will consider a more specific version of this Kelvin's problem where we consider this body again, but now we think of so maybe we let me see if I can rotate this thing. Okay, so what I'm saying is suppose I look at it in a slightly rotated fashion such that this blue colored arrow, it is now vertical. So it's not an exact diagram, but you understand what I'm doing here. Okay, so it's the exact same situation here physically. I'm just looking at it in a slightly rotated fashion. Next, what I will do is that instead of this kind of a general coordinate system x1, x2, x3, I will note or observe something special going on here. You note that this boundary here is completely arbitrary. Okay, arbitrary in the sense that I have just drawn it for the sake of visualization, but this boundary is not really here. This is way off into infinity. Okay, so what you must appreciate here is that there is a certain cylindrical symmetry going on here. So what I mean by that is that suppose you were to construct a cylinder around this this point body force represented by this arrow, and suppose you construct a cylinder like this. Okay, whose longitudinal axis coincides with this arrow. Okay, so no matter where you are sitting on the surface of this circular cylinder, the situation is going to look exactly the same. So what we mean to say is that there is no dependence on the angle. I mean, suppose you consider this particular line. So if suppose if I had to draw a line here, this horizontal line, suppose we say that looking from the top that this is and you consider another line here maybe. So suppose this angle is theta. Okay, so there is no difference between this line and this line, or you consider any other line, any other radial line like this all around it, it doesn't make any difference. Okay, so all of these radial directions, they are exactly the same. So let me clear up this drawing. Now, because of this kind of a nice cylindrical symmetry about it, what we can do is we can consider a cylindrical coordinate system, which is a much more specific thing to talk about, going from this x1, x2, x3 system. So we'll consider a cylindrical coordinate system where this direction is r, this direction is z, and since there is no dependence on the theta, we don't have to talk about it. Now this kind of a RZ plane, you can construct it at any theta. So as I had drawn earlier, so you consider any theta angle, you can have a RZ plane there. Now what I'm basically saying is that no matter which RZ plane you consider, it's going to be the same. Okay, because of this nice cylindrical symmetry or axis symmetry around this longitudinal axis. All right, now the immediate question is, some students may be thinking that all right, so effectively what we are doing here is it not saying that we are reducing this 3D elasticity problem to a 2D elasticity problem? The answer is a strict no. We are not doing that. Okay, although it may seem like that, we are not really reducing this 3D elasticity problem to a 2D elasticity problem. Just because we are talking about only the RZ plane, it does not mean that. And you will see that when you finally find out the various stress components. Okay, so it will be absolutely clear that this is not really a 2D elasticity. This is very much 3D elasticity. All right, so without talking anymore, let me actually get on with the steps of the Kelvin's problem. So just to reiterate before proceeding any further, or before starting, is that we are going to start with this general thing, then we are going to specialize to this thing, and then find our solution forms. All right, so let me go to the next page here. So solution of the Kelvin's problem using the Popkovich-Neuber representation. So to reiterate, what we had in the Popkovich-Neuber representation was we were dealing with two things. So one of them was this B vector, and we said that the solution of the 3D elasticity problem, it could be reduced to the solution of two sets of Poisson equations. So one of them was in this fashion. So del square B vector is equal to rho b vector divided by 2 into 1 minus nu and del square beta, which was a scalar, that beta was that del square beta was equal to minus x vector dotted with rho b vector divided by 2 into 1 minus nu. This rho b vector here, this is the body force. So this is the general representation of the body force, as we have been seeing from our stress on our chapter on stress. But now what we are going to say is that this body force must be made specific to the problem at hand. So the problem at hand is this Kelvin's problem. Here the point where this thing is acting, this body force is, this point body force is acting, is this xi vector. And since this is a point vector, since it's a point body force, what we can do is, and let's say the magnitude of the force vector representation of this is like p vector. Okay, so that's so in this equation what we are going to say is that this rho b vector, it gets substituted by this p vector. But it is not enough to write it like a p vector, because that would imply that this p vector is acting at any general point within the body. So no matter which x vector you choose within the body, this p vector would apply. But that is not the case. That p vector is being applied only and only at the position x vector is equal to xi vector. And how do we specify that? Using the Dirac delta function, 3D Dirac delta. So if you write it like this, then it means that according to the definition of the Dirac delta, if you refer back to the previous lecture, it means that whenever our xi or this x vector is not equal to the xi vector, then this entire result is equal to 0, which is exactly what you want. So and wherever this x is equal to the xi vector, you have that concentrated body force acting. Okay, so this is how we convert the general statement of this Popkovich-Neubauer representation to something specific to our problem. In a similar fashion, for this second equation also, we write it like, so we replace this rho b vector by this p vector with the Dirac delta. So identifying this particular thing, okay, so this is the most important preliminary step. Okay, now all this hard work that we have been doing in discussing the mathematical precursors, the various representations and all these things, it has been leading up to this point. Okay, so what I'm going to write next is directly the solution that we are going to need. Okay, so you note that both of these, so del square b vector is equal to this entire thing. It may look complicated, but ultimately this del square b vector is equal to this thing. It basically means that this is a Poisson's equation. This del square beta is equal to this thing. It's complicated looking, but it is after all a Poisson's equation. So if it is a Poisson's equation, we should definitely be able to write down the particular solutions to both these equations, this del square beta b vector and the del square b beta, using the forms that we had discussed in the previous lecture. Okay, so what we say is that the particular solutions to these Poisson's equations are in this form. So for the first equation, the particular solution is so you note that we need a minus 1 by 4 pi. Let's write that minus 1 by 4 pi, and then within the integration we'll have this this entire thing, p vector delta So I've simply written the right hand side of this equation. So this is like the small f vector which was present in the general form of the Poisson's equation, and then I need to write this x vector minus so I have to be a little bit careful here that this x vector, this is replaced by the x dash vector, and what I have in the denominator is this x vector minus the x dash vector, just like we had done in the case of the example problem at the end of the previous lecture. And this integration is with respect to the x dash vector. The cube represents that we are integrating over the entire volume of concern. Of course, this is an infinite volume, but no matter, we can proceed in exactly the same fashion. So what is the result of this? So you understand that here this p vector, it is a vector but it's a constant. So exactly like the example problem that we had done in the previous lecture, so this can be taken out of the integration. So also this 2 into 1 minus nu can be taken out of this integration, and what will be left within the integration is this delta x vector dash minus xi vector divided by this magnitude. And so let me write that down. So this is 8 pi 1 minus nu, and I have within my integration Dirac delta x dash minus xi vector divided by this thing. So the result of this, okay, so all that I have to do in order to actually carry out this integration is to utilize the filtering property of this Dirac delta here, and we have already done this in the example problem. So it's exactly like that. So the result of this is simply this remains as it is from the previous step, and what we have here is simply the x vector minus this x vector dash. This gets replaced by this specific point where the point body force is acting. That's it. Okay, so you see this particular solution for the b vector, which is very much a part of the Popkovich-Neubert representation, that is a function of x vector, and here we have the dependence on the x vector through the presence of this term here. And note that this xi vector is just something specific which has been given to us as part of the problem statement, meaning that this is the point where the body force is being acting. So in exactly the same fashion, we can proceed with this second equation. The particular solution to that is given by, again we write the same thing. We faithfully follow the method which has been developed, and let the result take care of itself. So again, you understand that here I have to make a little bit of a correction, in the sense that in the numerator, whatever was an x here, that has to be made an x dash, and this also has to be made an x dash. So now the thing that I can actually take out from here is this p, but there is a little bit of a complication in the sense that there is a dot here, but we don't have to worry about it. you can understand that the result of this will be obtained by substituting in whatever the function is as present as a coefficient of this Dirac delta. In that function, wherever the x dash is present, we just have to replace it by the xi. Okay, so let me do that. So at one shot I can write my answer. So please note that there is another slight mistake. So there is already a minus here. So this minus is coming from the general form of the solution of the Poisson's equation. So there is actually a minus here also. So overall there is a plus here, and what we are obtaining is this. So again there is a 8 pi 1 minus nu, and in the numerator I don't have to write this 1. Rather, I'll just substitute this x dash vector by the xi vector that is dotted with the p vector, and in the denominator I have, just like before, the x vector minus the xi vector. That's it. This is the solution. This is my particular solution for the beta. Okay. Now that we have in our hand the particular solutions for this b vector and the beta, you would be naturally thinking that, okay, in order to complete the solution I have to find out the homogeneous part. But actually it turns out that we don't have to do that. Okay, so I'm not going to go into a formal proof of that, but at the end I will discuss why this is so. So for now I will leave out a missing link from here. Okay, so I'm deliberately leaving a missing link here. So the missing link is this. That how the particular solution which we have just written, how the particular solution becomes the total solution. Okay, so we'll come back to a little discussion of it at the end. It will not be possible for me to go into a formal proof of it, but I hope as engineering students you will appreciate the hand waving kind of argument that I will present to you. All right, so with this missing link still nagging at us, we'll proceed. So what we'll say is that using these two particular solutions only, we are going to construct our displacement vector. Okay, because you see these help us. So these are part of the Popkovich-Neubauer representation, but these themselves are certainly not the displacement vector. So what is the displacement vector? So let me go back to that representation from a couple of lectures back, and just write down the expression for the displacement vector in terms of this b vector and the beta vector. Appreciating again that I am actually writing I'm going to utilize only the particular solution parts. Okay, these of course will turn out to be the complete solutions, but more of that later. So this is u vector is equal to 1 by twice g gradient of the that's the beta vector. So that's just the beta plus dot product of x and b minus 4 into 1 minus nu b vector. Okay, now going forward, it will be easier if I just write this 1 by 2g. I mean, if I just multiply this thing here, okay, so I don't have to keep on writing this twice g in this denominator over and over again. So it's just a convenience. Sorry, I made the mistake again. So this should be just beta plus x dot p minus 4 into 1 minus nu b vector. Alright, so what I'll do is I'll just substitute this beta p and the bp here. Okay, so this is gradient. Directly utilizing what I have present here. So this is xi dotted with p divided by 8 pi 1 minus nu x vector minus psi vector. And I have next the x dotted with b, so this is my b. So all that I have to do is just, so this plus becomes a minus, Alright, so let me just check it once more if I've written it correctly. So if you just compare it here, all that I have done here is just dotting this thing, this numerator with the x dot, because I have this x dot b. Okay, so this entire thing is within bracket because the gradient is operating on this entire thing. And I also have this minus 4 into 1 minus nu, and there is this b vector which is this, so there is a plus here, then p vector divided by 8 pi 1 minus nu x vector minus xi vector. Okay, so this 1 minus nu cancels with this 1 minus nu, so overall what I'm getting is see, there is a little bit of a simplification that can be carried out here. So I can actually write it as x minus xi, x vector minus xi vector dotted with p. So I'll take this minus sign out of this gradient and write it in a slightly more compact form in this way. So you can already see that things are shaping up quite compactly here. Okay, let us not forget that this gradient is operating on the whole thing, and for the second term we have p vector divided by twice pi x vector minus the xi vector. Okay, now remember what we said earlier. We had said that for the solution of the Kelvin's problem, we are first going to start from this general kind of a situation where we do not where we keep this coordinate axis general, this x1, x2, x3. That is exactly what we have done by writing our entire thing in terms of this general x vector, and considering that the point body force is acting at this point xi with this position vector xi. Now, as discussed earlier, we are going to make it, we are going to change our viewpoint to this particular situation, where we take a very specific choice of this x1, x2, x3 coordinate system in the form of a cylindrical coordinate system. And as a further specialization, what we do is we choose the origin of our coordinate axis. As you can see here, this coordinate axis, the origin of this coordinate axis is coinciding with this point of application of the body force. The immediate implication is here is that what was xi here in this diagram, what was xi here, so here that xi becomes 0. Okay, because the point of application of this body force with respect to this cylindrical coordinate system is nothing but the origin itself. So xi vector is nothing but the 0 vector itself, the origin vector. Okay, so if we specialize to such a diagram, then our entire formulation will become much simpler. Okay, so furthermore, what we'll also note is that what happens to this form of this magnitude of this x vector. Okay, so let me go to the new page and discuss all these details. So now we change our viewpoint to let's call this figure 1 and figure 2. Okay, so let's say this is figure 1 and this is figure 2. Please note and be very careful that as far as the actual physical situation is concerned, because you see this coordinate axis, this choice of the coordinate axis, how you are representing all of this is just a mathematical choice, but the actual physics, it remains the same. So whatever was the situation here is exactly the same physical situation here. Okay, so we are very much still solving the Kelvin's problem. We just are making a nice, more convenient choice of our viewpoint. So we change our viewpoint to figure 2. Okay, so where our xi vector is equal to 0, you can put it as a 0 vector, where our x vector, this general x vector, what is it? This is r ER vector, so this is the unit vector along the radial direction, plus z EZ vector, which means that what was previously x vector minus xi vector magnitude, that is simply the magnitude of r ER vector plus z EZ vector, which is nothing but r square plus z square square root. So you see, things are shaping up to more familiar forms. So with this understanding, or with this change of viewpoint, how can we possibly simplify this expression? Okay, so let me copy this. Let me try to copy this. So this is my twice GU vector. So this becomes now minus gradient of, so this is simply this x vector minus y vector, as I've written here. This is RER vector plus ZEZ vector, dotted with, what is my P vector? So P vector, you note from my figure 2. So in this figure 2, this is P vector, Now with reference to this cylindrical coordinate system, this p vector is simply, here it is p vector is equal to p Ez vector, because it is oriented along the z direction. So that's what we are going to use here, p Ez vector. This will considerably simplify our algebra. So this 8 pi into 1 minus nu factor remains as it is, and as we have just seen this magnitude, it becomes square root of r square plus z square. And here we again have p Ez vector, and this denominator becomes twice pi into square root of r square plus z square. Okay, so we can make a little bit of a simplification here by noting by actually carrying out this dot product. You note that ER vector, or this ER unit vector, it is perpendicular to this EZ vector, EZ unit hat. So the dot product of that is 0. So what we end up with is this thing, Ez from a multiplication between these two, and Ez dotted with Ez is 1. So now you see what is happening here. What we can do is we can for clearer understanding of what is going on, and perhaps to simplify these expressions also, we can decompose, or we can consider the different components which are present here. So the component along the r direction and the component along the z direction separately here. So you understand that this u vector here, that is also in this fashion. So it is twice g ur er hat plus uz ez hat. So we just have to equate the coefficients of the er hat and the ez hat. But before that, we have to note that this thing, this gradient, that is er hat del r plus ez hat del z. This entire thing operating on whatever was present inside the curly brackets. So what we'll have is twice g ur will be equal to just the coefficient of the er on the right hand side, and that's going to be minus del r of this entire thing, pz 8 pi divided by 8 pi 1 minus nu r square plus z square, and we don't have any other term here. So let me get my page all right. Okay, so and separately the uz will have, so let me just write it here. The uz will be minus del z of this pz divided by 8 pi into 1 minus nu r square plus z square plus this entire term plus p divided by twice pi r square plus z square. Sorry about the clutter here. Okay, so what I'm interested in doing here is to proceed with this UR component. Okay, so just to get a fair idea of the kind of expressions we'll be dealing with, you see, for the purpose of this partial differentiation with respect to r, this z here is basically a constant, so it might as well come out just like this p, this 8 pi 1 minus nu can come out. So that's nice here. So of course, using something like symbolic Python in Jupyter Notebook, you can carry out these expressions. You can carry out can find out the answers to these expressions in half a second. Anyway, we'll just do it for manually here. Okay, so the result of this will be so this is like a r square plus z square to the power minus half. So we are going to get a minus half out of this, and this r square plus z square, this is minus half minus 1. So using the simple differentiation rules, and ultimately we have to differentiate this with respect to r, so this is twice r, and this twice will cancel with this 2 will cancel with this 2, and you note here this is just a minus 3 by 2, so and this minus and this minus becomes a plus. So ultimately what will end up with is this pz divided by 8 pi into 1 minus nu, and then this r square plus z square to the power 3 by 2. Oh sorry, this r is missing here, so I must put this r here. So this is pzr divided by 8 pi into 1 minus nu square root of r square plus z square to the power 3 by 2. This uz will have to do a little bit more hard work, because you see this this z is present here in the numerator, and the partial differentiation here is with respect to z. Now you have to note something very important here. Okay, so we have bypassed the discussion regarding the boundary conditions at the very outset. So if we go back to our figures, here, you should note the kind of boundary conditions which will be present here. So referring to this more general figure, you see, we really don't have a real physical boundary present here. And again I emphasize that this white curve that I have drawn here, it is only for the purpose of visualization, that there is some material here. Okay, but this boundary is not really present. It's present at infinity. Okay, so in these kinds of situations, we have to impose a very special kind of I should not say impose, we have the physical situation demands it that we utilize a very special kind of boundary condition, where of course the term boundary condition is very much within air quotes, meaning to say that it's more like a far field condition. So what we say is that at x vector tending to infinity, okay, the u vector is going to be equal to 0. Please note that I am specifying my boundary condition, or whatever this far field condition is, in terms of the displacement vector. I am not actually writing this in terms of the b vector or the beta vector, because those are some things which are part of just the Popovich-Nobel representation, which helps me to proceed with the solution. Ultimately, the problem that I'm solving for is to find out the displacement vector. So whatever conditions are imposed must be utilizing those things. Okay, so in these terms, what do you think would be the situation here? So try to think of it like this. So maybe if you proceed along this line, okay, so as r tends to infinity, okay, so as r tends to infinity, you would have such a situation that the components of the displacement vector, they turn to, or they tend to 0. Okay, so can we perhaps think along those lines and try to see what is going on here in the solution? This one component of the solution that we have obtained, what is going on here? So suppose you think of r tending to infinity. Okay, so what we can do is we can consider this ur and write the expression in a slightly different fashion. So we take this down below here, and now what I want to do is so let me just think. So what I wanted to do was place this r here. Okay, so I'll leave the r here. What I really want is to have an r square within this bracket. So that means I have to put a r cube here, so that I end with so alright, so I'll have a 1 by r square here, and I'll have a r square plus z square divided by r square here. Alright, which means, so this is z, this is 1 by r square, okay, so this is the form that I am interested in. So now if I take the limit that r tends to infinity, then my twice gur, that becomes equal to 0, because you see r tends to infinity here. So so this numerator, it tends to 0, and this denominator, this term, it tends to 1, because this tends to 0, this is 1 plus 0, so this thing tends to 1, this is just a constant factor, so this entire thing tends to 0. And you can just see that if you're sitting on the line z equal to on the longitudinal axis, then z is equal to 0. So of course, no matter how it doesn't really matter how far away from the point of application of the body force UR, the UR of course is going to be 0 on that line. So it gives us a fair idea that this solution that we have obtained for this, at least for this UR, and you will see a similar sort of thing happens with the UZ. So remember, this UR we obtained from this general form, and this general form in turn was obtained. This general form was obtained in turn by accepting the missing link that we were not considering any homogeneous part solution for this B vector and the beta. But what is turning out is this. So what is turning out is something very nice. Okay, and this is the part where I discuss something in relation to our missing link, but don't really go on with a proof. So what we are saying is that this solution for UR comes from the U considering figure 2, and this in turn comes from the U vector of figure 1, and that U vector was obtained just from the particular solutions, B vector, and so B vector P and beta P. So really what we have been considering all along, we have been considering, very strictly speaking, what we have been considering or working with is the UP vector. Okay, but you see, what is this thing solving? This UP vector is actually solving the original Navier-Lamy equations considering the body force, and it turns out the solution for this thing is such that it is solving, or it is satisfying, the overall boundary conditions for the displacement vector. So this is a very, very subtle point. Okay, so this U vector P is certainly solving the original Navier-Lamy equations. Sorry about the bad handwriting here. Is satisfying the original Navier-Lamy equations. Very importantly, the Navier-Lamy equations which include the body force. Of course, for this Kelvin's problem, this body force is nothing but the P vector, the delta x vector minus xi vector. But whatever this form is, it does include the body force. So it certainly satisfies those Navier-Lamy equations, and it turns out that this solution satisfies the far field conditions for the original U. It satisfies the far field conditions for the original U. Okay, so this original U was supposed to satisfy the Navier-Lamy equations, and it was supposed to satisfy these far field conditions, and it turns out that the particular solution that we are obtaining, that is also doing the same thing. Okay, so it's very, very nice here. So again, I'm repeating, the original U that we desired to find out, that was supposed to satisfy the Navier-Lamy equations, including the body forces, that is certainly being solved, that is certainly being satisfied by the particular solution itself. The extra condition that we wanted for the original U to satisfy was the far field boundary condition, which was that U must tend to 0 as we go away and away, far away from the point of application of the body force. And that condition, that far field condition, is very much satisfied by the particular solution itself, as we have just seen here. So at least from this illustrative case of this UR, we are seeing that far away from the point of application of the body force, it is indeed turning to 0. So it is as if this particular solution is not just a particular solution, it is the solution. Okay, which is why back here, if I can just go back a little bit, back here, this missing link. Okay, so this question that we had posed, how the particular solution becomes a total solution, that is where the explanation of the missing link is. Okay, this particular solution becomes the total solution because it just so happens that this particular solution certainly satisfies the original governing equation, as well as it satisfies the far field condition. So we don't have to worry about the homogeneous part at all. Okay, so with this explanation, the solution part for the Kelvin's problem as far as the displacements is concerned is done. Now what we can go on to do is from these displacement fields, from the answers of these displacement fields, we can find out the strains, and from those strains we can find out the stresses. And once you find out the stresses, you can do some verifications. Okay, and those are the kind of verifications which have been carried out in our textbook example. So we can do those things very easily now. All right, on that note, I will end this lecture. Thank you very much.